Welcome to Spring LIB.
Okay, in this problem we have incoming light traveling through a very thin single slit across a distance of 2 meters and arriving at a screen where an interference pattern appears, as expected, of a single slit. So we are given the wavelength of the light, lambda. We're giving the slit width, a, something quite small, and we're given the distance to the screen. We're asked to answer a number of questions relating to uncertainties in y components of momentum and the width of the first maximum. As you know, that for a single slit interference pattern, there appears a one large first maximum, followed by a first minimum and other maxima of decreasing intensity. In terms of equations we'll be using to solve this problem, we need to make use of some equations from wave optics, from single slit interference in general, namely this equation here, that if we use the angle to the first minimum, which I have listed, going from the axis to the first minimum, call that theta 1. The sine of theta 1 is equal to simply lambda over a. That's one result we will use. Another result is we can relate the momenta, py and px. Their ratio is the tangent of this angle, and I drew these two, and you can use geometric arguments to arrive at that relationship. And lastly, for light in general, we can say that the momentum of light is inversely proportional to its wavelength. So we can use the result P equals h over lambda. Much of how we're going to do this problem is following the book section. Much of the results. We're going to be using the constants c, which is of course approximately 3e to the 8, 3 times 10 to the 8 meters per second, and Planck's constant, h. So let's get started. Okay, so the very first thing we must do in this problem is we start with these two relationships. Start with the sine theta equals lambda over a. We can note that if lambda is quite small compared to a, which it definitely is, then theta thus is very small. So we can approximate this. We can approximate sine theta as simply theta. This is a small angle approximation. And we're left with this expression. Similarly, we can do the same thing with tangent. That for very small theta, this expression, tan theta equals py over px, is really approximated quite well by this. So we can combine these two results. Theta 1 is the same and appears in both equations, thus we can arrive at this expression, py over px equals lambda over a. So now we've related the momenta to our wavelengths and more importantly, the slit width. So the one property of the system that has nothing to do with the light in general. Good. And it will actually be better for us to reformulate this in terms of py, since we're trying to isolate py and its uncertainty. So we can say that py is equal to px with this additional lambda over a factor. And remember, the light coming out of the slit can either travel positive values of theta or negative values of theta. So the momenta is really best express its uncertainty. It can really be plus or minus these values. It can either be on the upper, to visualize, it can either be on this upper part of the center line or on the lower part as well. So we can call that the uncertainty. Thus, if we want to have an expression for uncertainties, we can simply replace our py's and px's by delta py's and delta px's. Well, I hesitate to box this yet, because we can simplify it. We can say that the momentum of the light coming out of the slit in the x direction is simply the total momentum, because we say that it's initially coming at the slit horizontally. So using our expression that momentum is equal to simply h over lambda, we can replace this by h over lambda, resulting in wavelength actually canceling out of the equation. And we're left with an expression for delta momentum in the y direction is actually independent of wavelength. It depends only on the slit width, which is kind of interesting. So that's our first result, important result. Now to complete the problem, we have to make use of the uncertainty principle, which simply stated the product of uncertainties for momentum in the y direction and location in the y direction is greater than or equal to h bar over 2. This is an expression of the Heisenberg uncertainty principle. At this point, we can plug in our known value for delta p sub y, the uncertainty and momentum in the y direction. So we can get an equivalent expression. Dividing over, we can isolate delta y. And doing a little bit of simplification, we can see that h bar is simply h over 2 pi. So that h in the numerator will cancel the h in the denominator. We'll be left with a over 4 pi. So you see that, so at this point we can plug numbers in. When we do this, we end up with very, very small numbers. We'll actually need one more page to do this cleanly. Or not. So the result for delta y comes out to be about 4.9 e to the negative 6 meters. So fairly small uncertainty. In momentum, it's a much, much smaller uncertainty. We have 1.068 e to the negative 29. Which is somewhat interesting. So that's it. We have found the uncertainty in momentum in the y direction and the uncertainty in the location in the y direction, which gives us an uncertainty in the width. So for this particular case, it appears that the slit width needs to be at a dramatically larger or smaller value to get larger results here. You can see how it scales. You can see that as the slit width gets increasingly small, the momentum uncertainty will get increasingly large. For this particular case, A is not nearly small enough to have very, very significant quantum uncertainty effects in this particular situation. All right. Thank you.